Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video about ZyBooks Section 1.9. It's titled Nested Quantifiers. So we're going to see statements with more than one quantifier that binds the variables in a single in a predicate. So again, I'll read this opening to you. If a predicate has more than one variable, right, each variable, every single one of them must be bound by a separate quantifier. A logical expression with more than one quantifier that bind different variables in the same predicate is said to have nested quantifiers. So the examples below show several logical expressions in which variables are bound in each. The logical expression is a proposition if all the variables are bound. Remember, if there are any free variables, it's not a proposition. You can't tell what the truth value is. But if all the variables are bound, then it is a proposition. Right? We saw that last section. So this first one, for every x, there exists a y, such that p of xy. See how x is bound by the for all, the universal quantifier, and y is bound by the existential quantifier. So both x and y are bound. In this second statement, you have for every x, p of xy. You see there's this variable in the predicate that is not bound to a quantifier. Right? X is bound to the universal quantifier, but y is not. Y would be free. So the first statement on top is a proposition. And you can tell me if it's true or false. This statement, you couldn't. Right, is not a proposition. There is an x and there is a y such that t of x, y, z. See, y is bound to the existential quantifier. Z is bound to this existential quantifier. X is not bound. X is free. Right. So again, this last one would be not a proposition. Okay, so let's look at just a couple of examples here. Is the variable y bound in the expression, you see, for every x, q of xy? Well, the variable x in the predicate q is bound to the universal quantifier, so x is bound, but y is not bound to any particular quantifier. So the variable y is not bound, it is free. This would not be a proposition. Is the following logical expression a proposition, right? So basically, are all the variables bound to some quantifier? We have for every z, there is a y such that q of x, y, z. Well, z is bound to the universal quantifier. Y is in this predicate is bound to the existential quantifier, but x is not bound. So there is a free variable, x. So that means that this is not a proposition. All right, hopefully pretty simple to recognize. All right, then they get into statements involving nested quantifiers of the same type. So if you have two, a for all, back to back like this, see for all, or there exists, you have two universal quantifiers back to back, or two existential quantifiers back to back. Now, if every variable is bound, then you have a proposition, right? It can be either true or false. All right, so I'm going to go to some paper here. All right. And we'll talk about these statements. I'll actually go through, I'll go through the first couple. All right. Maybe the first and the third one here. All right. So in the following question, the domain is the set of all non-negative integers. So that means 0 is included, right? 0 is not negative either. X times y, xy means x times y. Okay. So I'm going to write out this first. It is a proposition. Notice that the predicate. Right? The predicate is x times y equals 1. The predicate depends on two variables, and both those variables are bound to a universal quantifier. Right, so I'll write this out and we'll come to some paper. Okay, so they told us again the domain is a set of all non-negative integers, so 0, 1, 2, 3, 4, 5, etc. This statement is, for every x, for every integer, non-negative integer, and for every other non-negative integer, so this is just every pair, right? If I was writing this in English, for every pair, because there's two everys here, right? For every pair of non-negative integers, say call them x and y, the following statement is true: x times y equals 1. Right. Now when I say every pair, x and y can be the same number, right? This is representing every possible non-negative integer. This is also representing every possible non-negative integer. So they could both be the same or different, right? So let's see. Now again, there's no way in the world I'm going to be able to list off every pair of non-negative integers, but I could go over some examples, right? Now, in order for this to be true, right, it would have to be this statement, x times y equals 1, would have to be true for every pair of non-negative integers. So in order to show that this is false, you just need to give me one pair of non-negative integers that makes this statement false. X times y is not equal to 1. So how about if x were 0 and y were 0? I mean, there's one pair. And then, we have 0 times 0. Is that equal to 1? That is false. So right away I'm seeing that this is a false statement, right? Because this here would have to be true again for every pair of non-negative integers. So this is considered a counterexample, right? Because this is all universal here. Just an example of a pair of integers that makes this false, makes this whole statement false. And you could go through other pairs, x equals 0, y equals 1, x equals 0, y equals 2, and so on, x equals 1, y equals 5, whatever. Right? You could make up pairs of non-negative integers all day long. And you're seeing that, for a lot of these, the statement is false, right? Right, 1 times 5 equals 1, that's false. 0 times 1 equals 1, that's false. In fact, there's only one pair, right? There's only one pair of integers, non-negative integers, that makes this true, where x is 1 and y is 1. So going back to the assignment, right, the activity, this statement's false. Right? A counterexample would be, I gave 3 counterexamples: 0, 0, 0, 1, 1, 5, 1, 2. 1 times 2 is not 1. And yeah. Now you see how number 2 is similar. Alright, I'll just do number 2. Number 2 is similar. But instead of two, back-to-back universal quantifiers, we have back-to-back existential quantifiers. Alright. So I'll write that out and go to a piece of paper and show you some stuff. Alright. So now we have this statement. Now in English, this is saying there is a, again, the domain is non-negative integers. There is a non-negative integer x, and there is a non-negative integer y. So that means that there is a pair of non-negative integers, because the two back to back like this. So there exists a pair of non-negative integers, x and y. such that x times y equals 1. Now again, when I say a pair of non-negative integers, x could be any non-negative integer, y could be any non-negative integer, so x and y can be the same number. So we saw earlier, when x equals 0 and y equals 0, that makes the statement false, but that doesn't mean that this statement's false. This is not a universal statement. This is an existential statement. So in order to show that this is true, I only need to find a single pair of non-negative integers such that x times y, the product of those numbers, is 1. So x equals 1, y equals 1. There's a pair of non-negative integers, 1 and 1. And the statement x times y equals 1, 1 times 1 equals 1, that is true. And there I have found it. I have found this, this pair of non-negative integers that makes the statement true. So this is a true statement. Now you can read the other ones and be careful. Be careful. This statement here has a conjunction, meaning beloth of these have to be true at the same time. So let's say this one out loud. Right? This is there exists a pair of non-negative integers, x and y, such that both of these are true at the same time, right? And such that x plus y equals x, and y is not 0. All right. So you might think, well, if x were 3 and y were 0, you'd have 3 plus 0 equals 3. This would be true, but y I had to make y 0 there, so y is not 0 would be false. If you think about it, x plus y is only going to be equal to x if y is 0. So these can't both happen. This says that y has to be 0, this first part, and this saying y that can't be 0, that's a contradiction. Something cannot be 0 and not 0 at the same time. So there is no pair. I can't find a pair of numbers that both of these would be true, so this would be false. Right. Now if this is false, you see how this fourth statement is just the negation, and they talk about the negating. Remember the De Morgan's laws with negation? It works the same way when there's even more than one quantifier. Right? We talked about in section 1.8 negating a quantified statement. So this statement here, and I'll write this out as well. Okay, so we just got through, this was number 3, just got through saying that this statement was false. Let's look at the negation of that statement. The negation of, there is an x and there is a y, such that x plus y equals x and y is not equal to 0. Now remember, when you negate a statement with a quantifier, you can move that negation in to the statement here, actually right here, outside the statement, outside the predicate, and all the for everys become there exists, and all the there exists become for every, right? You saw that in last section. So the negation of this statement is going to be for every x and for every y. It is not the case that x plus y equals x and y is not 0. Now here in this predicate I'm negating this and statement, you can use De Morgan's laws further. This is logically equivalent to this. This is logically equivalent to for every x and for every y. Use De Morgan's laws. I put the not in. It is not the case that x plus y is equal to x. Is equal to x. Or, right, flip the and to an or, and then it is not the case that y is not 0. But instead of writing it is not, not x plus y equals x, we could simply write x plus y is not equal to x. or, and then instead of writing not y is not equal to 0, just write y equals 0. All right, and do you see how this statement here is the statement in number 4? All right, you can see that here. The statement I just wrote here at the bottom of my paper is the statement in number 4. So this is just the negation of the third statement. And the third statement we said was false. The negation would have to be true then. Right, you see it comes up, it's correct and all that. Let me get rid of the paper. Okay. Now again, you could also think, this is saying for every pair of integers, every pair of non-negative integers, the sum of the integers is not one of them, right? X plus y won't be equal to x, or y will be 0. Because if y is 0, this would be true, but this would be, if y is 0, this would be false, but this would be true, right? If this is an or statement. As long as one of these is true, the whole thing is. Okay. All right, then you have the part where you have alternating nested quantifiers. So, we saw 2 existentials in a row, 2 universals in a row. This is the other way around. This is like a mix of the quantifiers. So you could have an existential, then a universal, or a universal, then an existential. All right. And again, you can read through the examples here. I'm just going to go to and play this animation if you wish. Talk about this, existential player versus universal player. I'm just going to go to the activities and talk about, how are we looking at these. So number 1, right, the first quantified statement in this activity. Now this time the domain, right, is the set of all real numbers. So this time the domain is the set of all real numbers. All right, let me I'm going to write down the first one and we'll take a look at it. Okay, so I've written down what's going on in the first one. All right, again, the domain is all real numbers, right? So that's rationals, irrationals, all of them. Right? Here I have for every x, there is a y such that x times y equals 1. So this is in English would be for every real number x, right? Because x is representing a real number now. For every real number x, there is a real number y, which could be the same number, right? Because x could be any real number, y represents any real number. For every real number x, there is a real number y such that x times y will be equal to 1, right? Such that this predicate will be true. All right. So this is, I start off with this is any, so you pick any x you want. This is saying if I pick any x, I can find a y that'll make this true. All right, so another way to think about this is if you pick any x, we can find a y so that x times y equals 1. All right. So for instance, I pick x equals 2. That's a real number. And again, this is just an example, right? This is a universal statement. This has to be true for every real number. So just showing one example isn't going to be good enough, right? But I'm just showing you one example. If I pick x equals 2, then y would have to be 1/2, wouldn't it? Right? Because 2 times 1/2 would be 1. All right, so it's true for x equals 2. For x equals 2, I can find a y such that x times y equals 1. For x equals 9, y would be 1/9. 9 times 1/9 equals 1. I mean, I could do that all day long, right? Pick a real number, then do 1 over that number. Right? This is true for every real number except 0. What if I picked 0? Yikes. Right? 0 times any y equals 1 is going to be false. That is going to be a false statement. Because if you pick... So basically 0 doesn't have a number you can multiply it by to make 1. Right, but this is a universal statement. This has to be true for every real number. I started practicing. I looked at some examples. I'm like, oh, here's a counter example to this statement. Right, the number 0 does not satisfy this. Right, that's a real number to where I can't find a y such that x times y equals 1. Right, okay. So that is a false statement because of 0. Right, and they say if you pick x to be 0. Right, the universal player, they're calling it. The person who goes first. These all go from left to right. The person who goes first is the furthest left quantifier. Now look at the next one. Switch them. All they did was switch the order. Right, they switched the order. Right, so again, all they did was switch the order of the quantifiers. Now it's a existential first and a universal second. So in English, this means, again, the domain's all real numbers. The domain's real numbers. This says that there is a real number, x. Right? There exists, or there is a real number out there called x. There is a real number x such that for every real number y, x times y equals 1. Okay, so this means another way to think about this is that I can find an x, right? That means you can find. This is saying you can find an x so that x times y equals 1 for any y. Well, can you? Let's play around. How about when x is x equals 1 going to make this work? Let's see, is 1 times y equal to y, or sorry, equal to 1 for any y? No, it's not. Right? 1 times y equals 1 only when y is 1. How about when x equals, 10? I don't know. Is 10 times y equal to 1 for any y? No. And you could go ahead and play around with this all day long. X times y is equal to 1 only when y equals 1 divided by x, and x is not 0, of course. All right, x times y is equal to 1 only when y equals 1 over x, and x is not 0. So can you find a value of x that makes 1 divided by x equal to any number you want? No. All right. X equals 15, y would have to be 1/15th. That's the only number that this statement would work for. If x equals 75, y would have to be 1/75th, and that's the only number. It wouldn't, this statement wouldn't be true for any y, just one particular y. Right. So this is also false. I cannot find a real number to plug in for x such that that number times y will be equal to 1 for any y, right? For all y's, for all values. This is also false. All right, how about this one? There is a real number x such that for any y, x times y equals y. So is there a number x out there? Can I find an x? Can I find a number and plug it in for x such that x times y will be equal to y no matter what y is, right? For any y. Well, yeah, this time it's 1, right? If x were 1, 1 times y is equal to y for all y. So all you need, again, it starts off with a there exists. So this is an existential statement. I only need to find one example. If it starts off with a for every, then I have to show it's true for every, right? That's a universal statement. Here it starts off with a there exists. So I only need to find one. X equals 1. All right, if x is 1, then you got 1 times y equals y, and that's true for all y. And I'll leave for you to think about. And I've already talked about the De Morgan's laws with nested quantifiers. If you're negating existential or universal statements, negating quantified statements, you kind of just push the quantifier through to the predicate. Right? I'm sorry, not the quantifier. Push the negation through to the predicate. Right? And then as you do that, you change all the quantifiers, you switch them. So all the for alls become there exists, and all the there exists become for alls. And you can see that here. They even have an animation. I'll play at least the first part of this. See, when you negate 2 for alls, push it through that. See, it becomes there exists. And do it again. Push it through there. It becomes there exists, and then the negation goes, pushes all the way through to the predicate. And this statement is equivalent to the original statement. And you can do that with all of them. All right, and they do it with all the negations of all these nested quantified statements. All right, so I'll just let that one finish up, and you can finish the animation. They go through all the different cases. All right, so then the last thing here is just do that negation stuff. So this becomes for all x. When I negate this statement, it becomes for all x, for all y. So it's got to be this last one. I mean, you don't even do the rest of it. That's the only one. But then when you negate this not p of x and q of y, you do De Morgan's law. It becomes not p of x or q of y, not q of y. So just p of x or not q of y, which is what they have here, right? They show you the steps and all that. That's not too tough, I don't think. I feel like you can handle that. All right, so again, when you get these nested quantifiers, pay attention to what's coming first. Right? If a universal's first, then it's a universal statement. You have to prove the statement for all values of the domain. If an existential is first, then it's an existential statement, and you only have to find one example of a value of the domain for which the statement holds. And if they're both for alls, you're looking for, that means for all pairs. If they're both there exists, that means there is a pair, that kind of stuff. All right, so hopefully that was informative enough and you understood it. And again, I'm not doing all the reading. I'm hoping that you do all the reading, of course, and read carefully. Then you have your exercises. I didn't assign all of them in assignment 2, but you still have the solutions. You can see the solutions as you go through. Please work on them first. Before you look at solutions, try to get them on your own first, because you're not going to learn anything otherwise. And try, I'd say work on them all. The ones that are assigned and the ones that aren't assigned. Just for extra practice. That's the only way to get better at anything. And so that's it for section 1.9 on nested quantifiers. And thanks for watching.